Welcome to a deep dive into one of the most fascinating topics in modern optics: negative index metamaterials built from nanostructures. Imagine materials where light bends the wrong way, defying centuries of optical physics. This is the reality of negative index metamaterials. Let's begin with the fundamentals of how light behaves in normal materials. In all natural materials we encounter, the refractive index n is positive, meaning light slows down and bends toward the normal when entering a denser medium. The refractive index equals the speed of light in vacuum divided by the speed in the material, and this is always greater than 0. Here's standard refraction. Light hits an interface and bends toward the normal, following Snell's law with positive indices. Snell's law relates the angles. n1 times sine theta I equals n2 times sine theta t. But here's the key question. What would happen if we could engineer a material with negative refractive index? To understand negative index, we need to examine the electromagnetic properties that create it. The refractive index fundamentally depends on two material properties: electric permittivity and magnetic permeability. Mathematically, n equals plus or minus the square root of permittivity epsilon times permeability mu. To get negative n, we need both epsilon and mu to be negative simultaneously, which never occurs in nature. This diagram shows the 4 quadrants. Natural materials live in the top left with both positive. Metals have negative epsilon. The bottom right with both negative is where metamaterials operate. The critical question becomes, how can we engineer structures that exhibit both negative permittivity and negative permeability? The key innovation is using sub-wavelength resonant structures called split-ring resonators. Split-ring resonators are C-shaped metallic rings with a gap, typically hundreds of nanometers in size. Here are split-ring resonators. The gap is crucial because it creates capacitance, while the ring provides inductance, forming an LC circuit. The resonant frequency equals 1 over 2 pi times the square root of LC, just like an electronic LC circuit. At the resonant frequency, circulating currents in the rings create a strong, effective magnetic moment, giving us negative permeability. The effective permeability follows this dispersion relation, where F is the filling fraction and gamma is damping. Let's work a numerical example. For infrared light at 1 micrometer wavelength, we need ring radius around 200 nanometers, much smaller than the wavelength. The gap width might be 30 nanometers to get the right capacitance. For negative permittivity, we use plasmonic nanostructures that exploit collective electron oscillations. Metals like gold and silver naturally exhibit negative permittivity at optical frequencies due to free electron plasma. The Drude model gives permittivity as 1 minus plasma frequency squared over omega squared plus damping. The plasma frequency depends on electron density n, where typical values give plasma frequencies in the ultraviolet. For gold, the plasma wavelength is about 140 nanometers, meaning epsilon is negative for all visible wavelengths. Arrays of gold nanopillars create engineered plasmonic resonances, enhancing and tailoring the negative epsilon response. By combining split-ring resonators and metallic elements, we achieve simultaneous negative epsilon and mu. We arrange split-ring resonators and thin metallic wires in periodic three-dimensional arrays with spacing much smaller than wavelength. The lattice spacing A must be much less than wavelength lambda for the material to act as an effective medium. When both are negative, we take the negative square root, giving negative effective refractive index. The first experimental demonstration came in 2001 using centimeter-scale structures for microwave radiation. Since then, researchers have pushed the technology to infrared and even visible wavelengths using nanofabrication. Negative index creates bizarre wave propagation, where phase and energy move in opposite directions. In negative index materials, phase fronts move forward but energy flows backward, an anti-parallel relationship impossible in natural materials. The wave vector k and Poynting vector s point in opposite directions, giving negative dot product. This arrangement is called left-handed because E, H, and K form a left-handed triplet instead of the usual right-handed one. At an interface with negative index material, Snell's law still applies, but with counterintuitive results. Look at this dramatic difference. Light enters the negative index material and bends to the same side of the normal, not across it. Snell's law with negative N2 means the refracted ray appears on the same side as the incident ray. You might ask, doesn't this violate energy conservation? No, because energy still flows away from the interface. Energy flow is determined by group velocity, which points away from the interface, even though phase velocity is opposite. One of the most exciting applications is the flat lens, also called Pendry's superlens. Remarkably, a flat slab of material with refractive index, exactly -1, can focus light perfectly. A point source on one side creates a perfect point image on the other side, with the slab focusing all rays, including evanescent waves. For a slab of thickness d, the object and image distances both equal d, creating symmetric focusing. Unlike conventional lenses that require carefully curved surfaces, this flat slab focuses perfectly through negative refraction. The most revolutionary aspect is the ability to image features smaller than the wavelength of light. Conventional optics faces the fundamental diffraction limit. You cannot resolve features smaller than about half the wavelength. The resolution limit is lambda over 2 n sine theta, the famous Abbe diffraction limit. For visible light, this limits resolution to about 200 nanometers, no matter how good your lenses are. So how can negative index materials possibly beat this fundamental limit? The key is that negative index materials can amplify evanescent waves, which carry sub-wavelength information. Evanescent waves have imaginary wave vector component kappa, so they decay exponentially with distance z. These evanescent waves carry the fine structural details, but normally die away within a fraction of a wavelength. For transverse components exceeding K0, kappa becomes real and the wave decays exponentially. Inside the negative index slab, these evanescent waves actually grow instead of decay, recovering the lost information. This diagram shows evanescent wave amplitude, decaying below the slab, growing inside the negative index material, then decaying again to form the image. In principle, resolution is limited only by material absorption losses, not by wavelength. A crucial point: why must these structures be nanoscale? Why can't we build them at human scale? At human scale, with radio waves or larger, achieving the necessary resonances and loss characteristics is essentially impossible. First reason: the structure size must be much smaller than wavelength to act as effective medium. We need the ratio of structure size to wavelength less than about 0.1 for good effective medium behavior. For visible light at 500 nanometers wavelength, structures must be 50 nanometers or smaller. Second reason: plasmonic resonances that give negative permittivity only exist at optical frequencies for nanoscale metal structures. Third reason: ohmic losses in metals scale very unfavorably if you try to make structures larger. Losses are proportional to surface area over volume, which increases as structures get smaller, limiting performance. At the nanoscale, collective quantum effects and surface plasmon polaritons enable the necessary electromagnetic response. Let's work through realistic numbers for a practical negative index metamaterial. Consider a design for telecommunications wavelength at 1.5 micrometers in the near infrared. Our target wavelength lambda equals 1500 nanometers. Unit cell size should be about 250 nanometers, giving cell size over wavelength of about 0.17. Split ring outer radius of 90 nanometers. Metal ring width of 25 nanometers. Gap width of 30 nanometers for the capacitance. Using gold as the metal with thickness 40 nanometers. With these dimensions, we can predict the performance. Effective index around -1.2, plus or minus 0.3 I, where the imaginary part represents losses. Figure of merit, the ratio of real to imaginary index, around 4, indicating moderately low losses. Resolution enhancement of 3 to 5 times beyond diffraction limit. Creating these structures requires cutting-edge nanofabrication technology. Electron beam lithography can write patterns with 10 nanometer resolution, but is slow and expensive. Focused ion beam milling sculpts structures directly, but is even slower, good for prototypes only. Nano-imprint lithography stamps patterns repeatedly, offering better throughput for production. The biggest challenge is achieving perfect three-dimensional alignment over large areas with many layers. Multi-layer stacks with alternating metal and dielectric layers, each patterned with nanoscale features, are required for full three-dimensional metamaterials. Typical fabrication tolerance of plus or minus 5 nanometers, which significantly affects optical performance. Despite exciting promises, losses present fundamental limitations to metamaterial performance. First loss source: ohmic losses in the metal due to finite conductivity. Gold conductivity is about 4.1 times 10 to the 7 Siemens per meter at optical frequencies. Second, radiation damping, as oscillating currents and resonators radiate energy away. Third, surface roughness in fabrication defects scatter light and increase absorption. Typical quality factor Q of 10 to 50, much lower than atomic resonances which can exceed millions. Can we overcome these losses to achieve practical devices? Partial answer: incorporating optical gain media, like dyes or quantum dots, can compensate some losses. However, this introduces noise, stability issues, and additional complexity. Negative index materials enable many applications beyond just super-resolution imaging. First application: optical cloaking by bending light around objects using transformation optics. Light rays bend smoothly around a cloaked object and emerge as if nothing were there, rendering the object invisible. Second, perfect absorbers that trap and dissipate all incident light at specific wavelengths. Third, optical antennas and waveguides with unprecedented control of light at nanoscale. Fourth, enhanced nonlinear optical effects due to strong field localization in metamaterial structures. How do we know negative index materials actually work as predicted? First test: directly measure the refraction angle at an interface and verify it's on the wrong side of the normal. Second, measure phase advance through the material, confirming backward phase velocity. Third, the wedge experiment, where a prism of negative index material bends light the opposite way. A prism of negative index material bends light toward the thick end rather than the thin end, opposite to normal prisms. Fourth, resolution tests showing sub-wavelength features that conventional optics cannot resolve. Results have confirmed negative index behavior in microwave, infrared, and visible light regimes. Let's ground our understanding in Maxwell's equations, which govern all electromagnetic phenomena. Faraday's law, curl of E equals negative partial B partial T. Ampere's law, curl of H equals partial D partial T, neglecting free currents. Constitutive relation, D equals epsilon 0 times relative epsilon times E. And B equals mu 0 times relative mu times H. For plane wave solutions, Maxwell's equations yield the dispersion relation. Wave vector squared equals omega squared over c squared times n squared. Crucially, nothing in Maxwell's equations themselves prohibits negative epsilon or mu, only nature fails to provide them. Metamaterials achieve this artificially by engineering structures at the nanoscale.